in the project Space and Time After Quantum Gravity, as well as Beyond Spacetime. I'm very happy to present to you as a first visitor and speaker this year, Alexei Grinbaum, who works in the lab LARSIM at the French, Commission d'énergie atomique. Sorry?
Commissariat.
Commissariat à l'énergie atomique in
Saclay. À l'énergie atomique et aux énergies alternatives.
Oh, but that must have been added later on.
Yes.
Okay, anyway, so Alexei is a research scientist there, and he originally received his first degree in physics from St. Petersburg State University, and then moved to France to get his PhD at the École Polytechnique in philosophy of science, in Paris, of course. He works on foundations of physics, but also the ethics of science and technology, and he has published numerous articles, I think something like 60 over total or something like that. I'll only mention two books, a relatively recent one by the title Mécanique des étreintes, Implications quantiques, which appeared in 2014 with Encre Marine, and his forthcoming book, which is supposed to appear next spring, called Satanas Ex Machina, Délivrer l'intelligence artificielle du mal. Today, he will be speaking about how device-independent approaches change the meaning of physical theory. Please.
Thank you so much, Chris. Very happy to be here, and thanks very much for the invitation. Particularly happy to be speaking in this room of the Department of Ancient Studies with the map of Formalism, because it so happens that this is my first article on foundations of physics that has two terms in it in ancient Greek, one from Plato and one from Numenius. So I thought this is a very appropriate setting. I didn't expect the referees to let me publish Greek terms in a Foundations of Physics article, but it did happen anyway. So let's start, and I would like to start with a game. A game that, not a game played by ancient Romans, but a game that's been made famous by John Wheeler. Sorry, Wigner will come up with later. By John Wheeler. So John Wheeler is, this great visionary of the 20th century, who was a student of Bohr, but also a bit of Einstein's. Here's Wheeler with the busts of Bohr and Einstein in his office at Princeton. Wheeler, in one of his late articles in the 80s, and I really admired him a lot. Late in his life, as you probably know, he was interested in foundational questions about quantum information. So years before that, he was a teacher of Everett. So Wheeler has really played a crucial role in the foundations in the 20th century. So he publishes this text when he says, okay, well, look back. So this was in the 80s. He says, look back, we had this game on television in the 50s, and it was called 20 Questions. And this is how the game went. So people meet in the room, and then one person has to go up. So Chris goes behind the door, we shut the door, and we choose here between us some word. Let's say, I don't know, cloud. Okay? So then Chris comes back, and he can ask binary questions. And he needs to guess the word. So he asks binary questions, meaning the answer can be only yes or no. Does it have legs? No. Is it green? No. Can it fly? Yes. And so forth. And if you guess the word with less than 20 questions, then you win. Right, so maybe at the 19th or 18th question, well, Chris is very clever, so maybe at the 17th question, you say, this is a cloud. Isn't it a cloud? And everybody claps, and everybody's happy, and you're particularly happy because you won. And Willie said, okay, this is the television version of the game, called 20 Questions, played on American television in the 50s. But here is John Wheeler's version of the game. Well, still the same thing. Chris goes out behind the door, then comes back, then starts asking questions. You know, does it have legs? No. Is it green? Right. Can it fly? But an interesting thing happens. So the first question goes as before, and there's an answer. Does it have legs? No. And then the second question, is it green? And the person who has to answer, so the question is not to the group, the questions are to individuals. Oh, so one person has to answer. So Lorenzo has to answer the question, is it green? And he takes some time, maybe 30 seconds. He will not answer immediately. Okay? And then, I don't know, Vincent has the third question. Can you fly? And he will take a bit more, maybe a minute. And then produce an answer, and the answer will be, well, let's say no. Okay? And then each time, with each new question, the person who has to answer the new question is taking a longer and longer time to produce an answer. And then maybe after, I don't know, 19 questions, Chris says, is it a cloud? And everybody bursts with applause and clapping, and everybody is happy. Now, what happens, says John Wheeler, what happened in this game? Why did people take this time to think about these binary answers? Isn't it kind of simple? And the answer is, when Chris was out there, we had agreed here not to choose any word at all. We haven't chosen the word tub. We agreed here not to choose any word at all. So, how did it go? The first person produced some answer. Does it have legs? No. But then every other player, before giving an answer to Chris, had to come up with their own version of that object, of that concept, right? That would be compatible with all previous answers and give their own answer, and so forth. And that's why it had been taking so much time, right? Because every player actually had to be Chris, had to play the game for Chris, right? And at the end, well, it converged. So everybody wins, not just Chris, right? Everybody wins. And then the lesson that John Wheeler was drawing from this was about how this game is similar to quantum theory, that states don't pre-exist observation and on and so forth. What I would like to do with this game, this is the same game, but I see a slightly different lesson there. And this lesson is really about physical entities, that not only physical entities don't pre-exist observation, this is Wheeler's idea behind the game of 20 questions, but also here's an interesting question. Well, what if you don't win this game? So, what are those concepts to which all these answers refer to? Right? So every time you give an answer, you have to come up with some concept. But then if different players come up with different concepts because they don't tell others, and at the end there is no convergence, then there is no reason at all even to think that any object to which these properties pertain pre-existed or existed at all. So you see, at the end of the game, only this moment of convergence at the last question, when everybody says, yes, it was a cloud, makes everybody agree on what was the system in question. But if there is no convergence, the games can still go on, and everybody would have their own system. So this game is an interesting example of how you can make observations, make measurements, if you like, ask these binary questions without having a pre-existent system one for all. Right? There is no system which is shared by all observers in this game. So isn't something like this happening in quantum theory? And the answer is yes, if you look at device-independent approaches. So we'll talk about device-independent approaches, and this is a very hot topic in quantum mechanics. And I would say it goes beyond quantum mechanics. You will see that there really are important ideas for quantum physics in general, but also maybe for quantum gravity, for ways of going beyond certain problems that we have today in uniting space-time ideas with quantum ideas. So here's some sociology. You've heard today that sometimes you have to do sociology when you do science. Device-independent approaches 10 years ago didn't really, I mean, they existed. The first mention of this term goes back to 1998, quantum cryptography, but 10 years ago we didn't really have this massive rise of device-independent physics that we have today. So that's something to look at. What is device-independent physics, which is suddenly so important to quantum people, right? This is only quantum age. Definitely it has left quantum cryptography to go into quantum mechanics in general, quantum information in general. So I'm not going to talk at all about cryptography and the use of device independence in cryptography, but rather I'm going to give you a very general definition, which is really simple. A device-independent approach is an approach that looks at inputs and outputs that the observer registers. And between them, well, there is something. You don't know what is between. There is a box. And the number of inputs and the number of outputs is usually the same, meaning that every observer has an input, maybe choice of the measurement setting, and some output, so some reading of their apparatus. And these usually are in finite languages, so maybe binary, maybe 0, 1, 2. Anyway, they're rarely continuous. So they're usually symbols in finite languages, mostly binary. And all physics in a device-independent approach is contained in this probability distribution. The probability, the joint probability of the outputs given the inputs. Now, that's all. And you will tell me, what? Is this physics? How come it's physics? So indeed, we will ask this question very soon. What is really physical here? What's going on? We haven't said that there is any space-time physics or quantum physics, any physical theory that actually describes what is going on. Right? We haven't said that. We just said there are inputs and outputs, but why is this even physics? I mean, what is going on here? So we have to ask this question in a second. But before we do that, let me give you this, I would say, the first device-independent model which really has conquered the world, has conquered not only physicists but also philosophers of physics, is of course the Popescu-Rowley boxes. So Popescu-Rowley boxes, 1993, this fantastic paper in Foundations of Physics, which for years has, a bit like John Bell's paper, for years hasn't really been taken to be as important, and maybe 15 years later suddenly became the hottest paper ever published in the Foundations of Physics in the last decades. Now, what is a Popescu-Rowley box? Well, that's something that lets you go beyond quantum theory. Just to remind you, probably you know already what it is, right? There are two observers, two inputs, two outputs. So the inputs are X and Y, the outputs are A and B, and we have a probability distribution, probability of the outputs given the inputs, so it's a pure device-independent model. Well, there is a rule, which I'm going to give you in a second. And with that rule, we actually see that this model can accommodate a violation of Bell inequalities which is bigger than quantum. So if this square, well, let's call it a square, the green one is classical violation of the Bell inequalities, the red one is quantum, then there is something which is more non-local than quantum mechanics, and that is what PR boxes or non-local boxes can capture. So what is the rule? The rule is this. That's the only principle that we impose on a device-independent model. So it's a distribution of probabilities that obeys a certain principle.
And this word principle is very important. Where do they come from, these principles? So we'll have to talk about this. In a divisive independent model, it's not completely free, it's not like free lunch. There are principles, constraints. Where do they come from? So here is one. And that's called a no signaling principle. So the probability of A and B given X and Y is such that if X or Y equals 0, then A and B are the same with probability 1/2 it's 0, 0 or 1, 1. But only if both X and Y are equal to 1, then A and B are different with probability 1/2 it's 0, 1 or 1, 0. So this is how you write this mathematically. A plus B equals the product of X, Y modulo 2. So because these are zeros and ones, you can easily write your table and see what that is. Now, this is a no signaling rule in the sense that if you do the mathematics, then you find out that if you look at the output of just one party, A or B, it does not depend on the input of the other party. So Bob, by choosing his input, cannot signal instantaneously to Alice. So this is a no signaling principle, which is a constraint on non-local boxes. Well, we've heard the talk about principles in quantum mechanics before, so we will have as philosophers to ask the question of what these principles are doing. What kind of principles do we have here? So you see, here are some philosophical questions already. The first question was about these kinds of objects that different observers don't agree on. How come we still can do physics? What is physics? And the second question about the status of principles. So this example gives us a violation of the Bell inequality of the CH/SH inequality up to 4, and that's a maximal violation. You can go beyond that. So this is a maximally non-local model, which is very, very interesting for many reasons. So this paper has become really one of the foundational papers in quantum mechanics 20 years after publication. So I said, something happens in the box, and really we can call it the box world, or the box model. Something happens inside the box, but we are not given any description of it. We're just given a correct correlation between the inputs and the outputs. So whatever is in the box is of unspecified nature or unknown nature, but it's still somehow physical. The box captures unknown processes, but they produce at the end of the day a physical model. So maybe quantum mechanics, if we put on some principle like information causality, maybe a model that is post-quantum, so more non-local than quantum, but we can use it to study quantum physics. So, as I said, the sense of physical, in what sense is this unknown territory physical, is an interesting question that we're going to talk about. So, new meaning of physical theory? Physical theory about some unknown territory, unspecified boxes? We've heard it before. We've heard 100 years ago a debate about new meaning of physical theory. So it's not the first time we have to ask this question. So let me remind you that little debate that happened with Einstein when Einstein published in 1919 his famous distinction between principal theories and constructive theories. And of course, this distinction has produced such a debate that we're still there, and there are still people in Oxford who cannot, just cannot swallow that and still write papers about that distinction. And we love that, and we love that. That's very good. Why is that? Because it's still not quite clear to some people, as we see, how a physical theory can be a principal theory. Einstein famously wished for a constructive theory. He said that a theory at the end of the day should be, if it were to be explanatory, it has to be constructive. So he didn't say if it were to be complete, if it were to be universal. He said if it were to be explanatory, it had to be constructive for Einstein. And the big news from actually his own special relativity is that we can have a theory which is explanatory and a principal theory, not a constructive theory. The debate is open, and I'm not going into that debate. That's a big topic. What is today in relativity constructive or principal? I'm not touching on relativity here at all. What I would like to do here is to underline really this idea about understanding, about explanation. While Einstein was wishing for more, he was eager to have a constructive theory, but this never came. Right? This never came. And we believe today that we understand physics with a principal theory. We understand what is going on with a principal theory. That's something that Einstein thought would be bizarre, maybe even impossible back in those days. So that debate on new meaning of physical theory has led us finally to this idea that we can explain things, we can understand things with a principal theory. Well, now, what if in our box models, in our box world, what if a specification of what is inside the box never came? Wouldn't it still be a physical theory without specifying what's inside the box? Well, maybe, but there is one thing that we need to add to it, and that is this story about principles. Remember, the box is not only the inputs and the outputs, it's also the constraints, the principles that we put on as constraints on that box. So we just saw an example of a no signaling principle. And it's not a coincidence that Einstein was talking about principal theories, because again, these principles which act as constraints are his idea. Originally, this is what we have in special relativity. Einstein says the principle of relativity is a principle that narrows the possibilities, or in other words, it's a constraint on possibilities. And we've seen this before, once again. So you see, device-independent models are not really a novum in such a big sense of the word, because we've seen many things before. So we've seen principles as constraints before. Where? Well, in the body of work on axiomatic reconstructions of quantum theory. So just to remind you, this was my topic 10 years ago, or more, 15 years ago. So to remind you a couple of examples, well, here's your hero, Mr. Rovelli, who you have on your desktop. Our friend Carlo says, well, quantum mechanics will cease to look puzzling only when we will be able to derive it from a set of simple physical assertions of principles. Right? So he wants these principles to have a constitutive role, and he's right. It's a good formulation, I think, of what the reconstruction program is about. But the reconstruction program begins way back. Just to remind you, years and years, decades ago, we had these sorts of reconstructions. So Mackey in 57 had a very mathematical idea, or Ludwig, much later in the 70s, had a very mathematical idea of what it is to give principles for quantum theory. This is not what, these are completely incomprehensible unless you go deep into the mathematics. This is not for being read, this is for being admired, right?
It's also pretty small.
Yes. But this is to contrast. The reason why I'm showing you this is because I want to contrast this slide with this kind of thing. So Lucien Hardy, when he gives his principles in 2001, in his famous paper, he says, well, I have 5 principles. Here are the names. Probabilities, simplicity, subspaces, composite systems, continuity. So what is quantum mechanics? Well, it's some theory about probabilities, with composition rules, with some continuity assumption, and that's basically it. And take a simplest one. Right? So we have a much better idea of what quantum mechanics is about, what are the physical principles. And later on, so this was still a complete reconstruction. So people were trying to reconstruct the entire body of quantum mechanics from principles. But later on, we gave up on complete reconstructions. And nowadays, people are working on looking for principles for specific features of quantum theory. So for example, principles for the Zerelson bound that we were just talking about, the Zerelson bound of Bell inequalities. Where does it come from? We don't want to reconstruct full quantum theory anymore. That's not the problem. The problem is find out a physical principle which is responsible for the 2 square root of 2 in this HSH inequality, the Zerelson bound. So there are different versions, different proposals today in the market. None of those is perfect. None of those has won. So that's an open question today. But you see, these principles have evolved very much. Even within quantum theory, we've started with extremely mathematical formulations. We've arrived at something which is quite different. We're looking for a physical principle that will give meaning to a particular quantum feature, to even a definite quantum feature that defines quantum theory in a landscape of various alternative models. And here's my first example, and probably the longest example that I want to take of a device-independent model that uses principles, in particular node signaling, to ask a novel question which will be also very relevant, I think, for quantum gravity. And this is the problem of causality. So this framework has been developed by Kiribella and by Bruckner and Doreshkov independently, but let me tell you very quickly what this is about. I don't know if you've had any talks about it here before. So called indefinite causal order, indefinite causal orders. So what is an indefinite causal order? We have Alice and Bob, 2 observers. So here are different possibilities of their positions in space-time. The process can involve in their labs from the input to the output, can involve simultaneously. There can be a common cause, there can be a causal loop, or there can be what? A superposition? We don't know who is first, who is second. We don't know if Alice is before Bob or if Bob is before Alice. Can we put this information in a quantum superposition? And the answer is yes. Can we avoid contradictions? Can we avoid causal loops? And the answer is yes. So if we work with only 2 observers, it is possible to ask a puzzling question. The following question. Can it be not that Alice is before Bob or Bob is before Alice, but that this information on causal order is itself quantum, is itself in a superposition? That's something that quantum mechanics in principle allows, but space-time theories don't really allow. What is very interesting, and that's a Swiss result, so happy to quote some Swiss scientists. Armin Baumeister was the first to work on this problem for 3 parties. And he showed that provided a certain distribution of probabilities, which can be even classical, not even quantum, just a classical distribution of probabilities between the inputs and the outputs of 3 parties, we can have a situation when it's impossible to assign any predefined causal order to these parties. So we have Alice, Bob, and Charlie with certain inputs and outputs, certain probabilities of inputs and outputs, fully classical, but no causal order. We cannot say who is before whom. There's no way to do so. And that's a bizarre situation which I think connects this problem to quantum gravity. So, I'm not going to talk about the technical results here. I'm just going to show you once again this picture, and look at this picture. What happens here, there are 2 labs, 2 parties, Alice and Bob. As I said, there is an input and an output. So there's a Hilbert space here at the input, and a Hilbert space there at the output. Right? And we look at the tensor product of all these 4 spaces, and then we do some calculations, and we obtain this indefinite causal order. And that's not what I'm going to look at. I'm just going to look at this picture. What is a party, by the way? This box here, we call it a party. How do we characterize it? How do we characterize these boxes? So here is a box, like this. It has an input and an output, right? So Hilbert spaces. But In what sense can we say that this is a local lab? That this is the lab of Alice's, where she kind of opens a little window, lets some system in, and then the system is measured and flies out. But out to where, or in from where? And there are several problems with treating these parties as local labs. Why is that? Remember that there is no global temporal order. Time is only defined locally from one input to one output for Alice. For Bob, it's something else. You see, this is not parallel. There is some other time, local time axis. There is no global time here at all. There is no global order. So, if we want to ask the question, well, can we read this as a system coming from the environment into the local lab and then leaving into the environment, we have a problem, because this environment lies outside space-time, is described as a whole by the process matrix. Sometimes, actually, it so happens that a system can enter twice the same lab, which never happens with physical environment. So definitely, thinking about this whole thing in terms of local labs and the environment is only a metaphor. That's not fully correct. It's a nice shortcut, because this is how we're used to thinking about these boxes. There is a system which sits in the box, right, and gives us an input and an output and then flies out. But thinking about this as a system has some issues. We cannot do it consistently. We run into these problems of temporality, of double passes, and also of three parties. If we want to generalize this thinking to three parties, it just doesn't work. So, well, what we see here is that really inserting this talk about systems into this device-independent model of causal orders is just a metaphor. It's a useful shortcut for us. But you cannot do this consistently, seriously, like with all the implications of what it means that a system enters the lab and so forth. So, here's the first idea. In a device-independent model, yeah, we can talk about systems, but not in a rigorous way. It's a useful shortcut. It's because we're used to that. So it's not completely wrong, but it's never fully consistent. So if you want to be fully consistent, what we have is a model which doesn't have systems. It's doing physics without systems, if we ask for full consistency, full rigor. And only because it's useful, we call it a system. So let's see if this idea can be developed and can be seen on some other examples. And the answer is yes, but before we look at other examples, I want to take some time to go back to the 30s, to history of physics, history and philosophy of physics. So you remember that story very well, right? Any course on philosophy of physics discusses realism and why we cannot have entity realism in physics anymore. So Einstein famously wanted in the PR article written by Podolsky, but also in his correspondence, which he wrote himself, I hope, he wanted famously to have real systems, real objects. So he says in this letter to Schrödinger, for example, which I quote here, he says, I want to have real systems. And EPR, as you remember, has even a criterion for an element of reality, right? Element of reality, but this is Podolsky's language. So we know from Bell inequalities, from Kaufman-Steger contextuality, that entity realism is problematic. That we cannot have these entities, real systems as entities in the world. And on the other side of the spectrum, you know, people like Dirac at the same time were talking about physical entities. Well, this is a bit more subtle, I would say, because physical entities are really theoretical entities. We're not talking about here about real objects or real systems or elements of reality. Dirac is not talking about reality. He's talking about entities in the theory. Physical entities which can be at least theoretical entities. And something interesting happens with device-independent models. This is the first time ever in the history of physics when we can contemplate a possibility that not only the real world, But even the theory itself will have no entities. There will be no systems, not only as representatives of entities in the real world, but also as theoretical constructs as such. So this is more, what I'm talking about with device-independent models, is definitely more than the demise of entity realism. Even within a theory, it may not exist. But what exists in a theory if this old mode of thinking about systems doesn't apply? Well, we have a cool idea from Bob Kuke, who says in one of his many articles on categorical quantum mechanics, he says, well, why don't we think about systems as lines or wires between boxes in some symbolic diagrams that connect inputs and outputs, so various operations on the observer's information. So this is a purely schematic, diagrammatic meaning. Systems are these things that live on these lines or wires between boxes. In this sense, we definitely have an idea that, yeah, we can maybe look at some wires or lines in diagrams and say that they correspond to maybe a photon propagating or an electron being measured, but maybe some other lines will not be amenable to such an easy translation in terms of measurements in particular systems. So I call this a new mode of thinking about systems, a formal way of thinking about the systems as lines or wires. And now my second example, remember our intuition on the first example was that systems in a device-independent approach are handy metaphors for physicists, but definitely not there if you look at the details. So here's my second example where we'll see once again how it works. This example was invented by Miguel Navasquez and company, mainly by Miguel, and he published it in, I think, his PhD, originally with Antonio Acin in Barcelona, then it still works in it, even today. And this is called almost quantum correlations. So that's very easy. What you see here are two columns of definition, which are identical except for this one item. And these are two versions of how you compose systems. One is quantum mechanical. You have two subsystems, and you take a tensor product. That's how quantum mechanics composes subsystems, tensor product. But let's look at a different alternative. Let's look at an alternative where we don't have a tensor product of operators, but we look at values, so a weak version, we look at their values on a particular state, and we require that any permutation will give us the same value on any state, right? So that's not the same as tensor product, is it? Well, it's an open question. Is there any gap between these two definitions? Well, definitely if we measure this tensor product with a permutation of operators, because the tensor product there is symmetric, so we'll get the same value. There's no problem. But here, will this condition produce the same result as this condition or not? And Miguel showed that not. It will not. So if we look at this graph, there are some quantum correlations which are green here. So this is a part of the polytope of correlations. This is classical, this is green, quantum. There is some area, so this is non-signaling Pierre box, as before, we've seen that. But then there is some area here, which is almost quantum, but not quantum. And that's where we can find correlations which obey Navasquez's almost quantum axioms, and not the usual quantum axioms. So it's almost quantum, but a bit more than just quantum. And
what's P?
This is calculated by semi-definite programs. So these are borders. So this is a border that comes from some semi-definite limit of semi-definite programs that calculate this border for us. So what you do here, you have different inequalities. So the semi-definite programs are really linear inequalities being pushed in different directions. So you have all these things that are pushing from the outside, being pushed here, and this is how you form these borders. So this is a limit of these semi-definite programs. This is how we characterize this set Q tilde of almost quantum correlations. That's a technical issue of how it works. So, philosophically, we don't want to look at the details again of mathematics. Philosophically, we want just to look at their definitions. And we find, unsurprisingly, what you've already seen in the causal orders example, we find that it's handy to speak about systems. Right? So, Navasquez, for example, himself speaks openly about subsystems. So look at Alice and Bob and their respective subsystems, and then combine them and, well, maybe get almost quantum correlations. But that's the old mode of talking and thinking. That's really a metaphor. No, why is that? Well, because if you seriously, and I think there's really, he is a very sharp and beautiful writer, Matthias Fritz. And I admire his writing, really the way he writes his articles very much. He's a very good mathematical physicist. So he says, well, wait, we cannot really talk about subsystems here at all. It's a metaphor, but not more than a metaphor. Because whenever we talk about subsystems, subsystems compose through a tensor product. Well, here we don't have a tensor product, we have something else. So we should rather, if we want to be serious, we should talk about a global algebra, right? And then ask, under which conditions this global algebra factorizes as being about subsystems. And then there will be other conditions under which it doesn't factorize as being about subsystems. So there's a beautiful phrase here. It seems that the correct question would be, when does a physical system behave like it were composed of smaller parts, rather than how do physical systems compose to a composite system? Now, what is the lesson here? The lesson is that we can ask this question, under which conditions do subsystems that make sense? Do subsystems appear? And if we just forget about the prefix sub, under which conditions in this global algebra that deals with inputs and outputs and an algebra on the inputs and outputs, under which conditions can we interpret this as being about physical systems? And maybe there will be conditions under which it is interpretable, and some other conditions under which we can still do physics in this big algebra, but it cannot be interpreted as being about systems. So here is the final result of our philosophical intuition that we had in the first example. Indeed, fully rigorously, we should say that a device-independent approach is an algebraic framework which is not about systems, but under some conditions that we can explore, it will be interpretable as being about systems. And that will be a new physical question. So if we have the right kind of mathematics for this physics, then maybe we'll get a right answer. And Navasquez actually wants to have the right kind of physical theory. He says, what these almost quantum correlations, what are they about? What kind of physical theory? I don't have that answer, please give it to me. So he's still looking. But we'll look at the mathematical framework only, not at the final answer, which we don't have. And the mathematical framework here is really an algebraic framework in the language of languages, if you allow me that phrase. So what does it mean? We have inputs in some alphabet. We have outputs in some alphabet, maybe the same. They are finite cardinality, they're finite alphabet, so maybe 0 and 1, that's it. We have some algebra on these things, and we put some constraints, like no signaling, or maybe some other constraints if we want. And the question is, well, under which constraints do these things behave as if there were physical systems in those boxes? And maybe under some other conditions, they will not behave as if there were systems in those boxes. But we will still do physics, and this will still be physics. And that's an interesting lesson, and I will stop my formal mathematical part here, although I have some answers in an article published in 2015 to that question. But I will now stop the mathematical part, and to conclude, I will go back to the philosophical part. And I will say, we've just done the same kind of thing, the same kind of revolution as Shannon had done to information theory. Now, what is that? Well, what Shannon said was, strings are not about something. There is no semantics. Strings are information. It's not information about something. Forget semantics. Work with the formal notion of information, said Shannon. We are saying these inputs and outputs, these are strings of symbols, not about some physical system. There's no semantics. Maybe under some conditions it will make sense to speak about some semantics. But in principle, no, there's no semantics. So just like Shannon, this question of semantics gets evacuated from the theory. It's not there anymore. So we've done to physics what Shannon had really done to information theory. Well, is that really, really, really new? I think, and of course, I think that, Niels Bohr had an intuition about that. And we've heard today a lot about the word intuition, but I would like to add to that. That for me, the thing I like to say is really, Niels Bohr is a bit like Jesus Christ. You always have to interpret what he says, because you just don't know what it means if you didn't interpret. You have to interpret every word that Bohr said. So here's something that Bohr says. He says, well, look, physics is really a symbolic structure, and we want in quantum theory some kind of symbolism, some kind of symbolization if we want to express quantum theory. And he never says that this is the Hilbert space. Never, ever. He says, we want some symbols, some symbolization. And then the use of mathematical symbols will secure an ambiguous definition of objectivity. He writes very late in his life. And we can go, there's a long discussion of Bohr in the article, we can go into these details, but I take it as quite significant. He's talking about the need for mathematical symbols all the way to the 40s and even early 50s. And we have Hilbert space there since von Neumann. And he's not buying that, right? He's saying we need some symbols. And, well, maybe we now have an answer from Mr. Bohr. Maybe, this talk about languages is even more fundamental than the ideas about Hilbert spaces and so on. Well, I will not remind you that von Neumann himself was very unhappy with Hilbert spaces. I will not remind you that Bohr had talked about languages a lot, right? You remember that he was not talking about formal languages, but he was talking about the importance of common language for expressing the results of measurement and for reaching this, obtaining this unambiguous communication between observers. But I will not go into that, although it's a very interesting discussion, so maybe you want to raise that. I will just tell you that Everett had some kind of intuition too. You see, everybody had their intuition. And Everett's intuition was, so it's in his main paper, right? Before he even speaks about branches and stuff. Remember, he never spoke about many worlds, he spoke about branches. Before he even goes there, he's trying to give a definition of observer. And he's probably the first, I would say, who gives a definition of observer in information theoretic terms. Remember, before him, we had a big debate on consciousness. London Bauer, 1937, right? Wigner and all these people in the 40s. Does observer have consciousness or not? Comes Everett and says, observer is anything that possesses memory, and that's the definition of observer. If there's memory, then you can be an observer. What is memory? Well, memory is something that correlates with states and keeps that information. So Everett was the first to give this definition of observer, and I would like to conclude with John Wheeler, who once again was Everett's teacher. I told you that at the beginning. And he writes in his notebooks late in his life, well, not so late, in the 70s, by the way, not very late in his life, he writes something quite interesting. So this was still the stage when we had quantum logic, when people were working in that area in quantum logic, and John Wheeler says something quite interesting. He says, well, we're trying to have a view of physics which is not a machinery, so it's not a constructive theory. It's not a theory of some kind of matter. It derives from some principles and observer, participant, and so on, doesn't matter. And he says this fantastic phrase, the propositions, so the elementary building blocks of his view of physics, are not about anything. And when I read this, and we had this debate with Chris Fuchs a year ago, a bit more, I was really astonished. Wheeler, before we even had any quantum information, before we had any informational approach in physical theory, he would say, okay, the propositions are not bearing any semantics. They are not about objects, they're not about systems, they're not about anything. And that's a great visionary. Only we can say that. So once again, let's admire Wheeler for being a precursor of device-independent approaches and this philosophy of how you do physics without systems. And on that, I would like to conclude.
So I guess I have a bit of a question, which is, I couldn't quite follow about.
Wait, can you make it lower? 1 second, Nick. 1 second. Just a little, yeah, too much, yeah, because it's. Okay. Sorry, yeah.
Okay, we didn't hear you. You're silent. I didn't hear everything then.
Yeah, just say it again.
Yeah, we've got no sound right now.
Okay. Well, it's good for us, so say it again.
Okay.
Good for
us.
us.
I get how the different pieces of the talk fitted together, and so sort of, or some of them didn't. I mean, I think maybe it was coming clearer towards the end. But in particular, there were a couple of examples. So right at the beginning about the non-locality, and then when you were talking about tensor products, where you were talking about systems that were almost quantum mechanical, but not quite quantum mechanical. But I didn't. So that's on the one hand. So that seems like a sort of premise, or a reason for adopting this approach. Is that right? And then it's the approach itself that does away with systems. But is there anything intrinsically in that idea of expanding quantum mechanics that's non-system-like?
Yeah. So can you hear me now? Yeah, you can hear me, right? Can you hear me? Say something, please. Yes. Okay. Good. Yeah. So I've chosen to speak about examples of device-independent models in the area of foundations of quantum mechanics. That maybe is not a very good choice because I've skipped the entire development on device-independent models in the area where they originally came from, which is quantum cryptography. So before we even talk about post-quantum models or how you can go beyond the Churlson bound or things like this, these are questions in foundations. Actually, today they're also in cryptography, but that's very late, a very late development. Originally, device-independent models have been developed for dealing with a question that I haven't mentioned at all, and I should have, which is the problem of trust. And this is one of the key problems in quantum theory. I'm talking about it at length in the paper, and this is what the problem of trust is about. In quantum theory, it is assumed that your measurement device will measure a system that you believe it will measure. If you're measuring the polarization of the photon, you trust your measurement device will measure photons. If you're, I don't know, measuring an electron or something, You trust that those systems that you will be exploring in your measurements will be electrons. So the problem of trust in quantum theory is really a fundamental assumption, and I'll tell you why it's a problem. First, it's an assumption that the preparation and the measurement are performed on those degrees of freedom that the observer thinks they are performed on. So if what the system is known, what does it mean what the system is? What the relevant degrees of freedom are is known in advance. Maybe the state will be different. The state can be unknown, but the system itself, we know it's a photon in an unknown state. Now, this problem of trust is a problem in cryptography. In cryptography, sources may be influenced or even prepared by sources of systems, prepared by adversaries. So you cannot trust your source. You don't know if it's giving you photons. You're going to measure polarization, but maybe it's sending you something else, not really photons, maybe some three-level systems or whatever, who knows? So how do you deal with this problem of trust? You cannot trust your source. So people in cryptography, since, well, really 20 years ago this problem has started, and since then they've developed methods for turning these adversarial sources into sources that can be trusted. And these go through different tests and so on. So this is where device independence comes from. And most papers, of course, on device independence are still papers in cryptography, because we want to work in cryptography with untrusted sources. So before we began expanding this device-independent thinking onto Bell inequalities, onto various foundational questions, they came originally from cryptography and from this problem of trust, which in quantum mechanics is just an assumption. So that's why I'm guilty in not having told you anything about this at all. It would have been a whole different development. But I'm taking here device independence in its incarnation in the foundations area, whereas it originally, of course, is not coming from there.
So, do you have another question, Chicago? Or not for now?
Maybe I'll just follow up. So, is it the case that, you know, the examples themselves that you were using to introduce the device-independent quantum mechanics, you know, by themselves point to system independence? I guess the one, or the, you know, getting rid of systems. I mean, I guess the one about tensor products has a fairly direct bearing on the question. So what about the question about I've forgotten the Rohrlich and I forgot who the other guy's
The causal orders
name was. Does that show something just by itself, just that sort of possibility about device independent? Not about device independent.
being without systems?
Does it somehow put pressure on the notion of a system? Because I don't see that quite so much.
Yeah, so these different examples, yeah, they relate differently to this idea. So I think the sum total, what I'm trying to say, that the sum total of these different examples is pretty convincing, but they are of different degree. So the example of almost quantum correlations is quite straightforward. The same, as you said, the same kind of argument actually also applies to yet a different example in the paper, so we're not talking about that. But back to causal orders. I mean, if you read the early papers on causal orders, they're really phrased in the language, in the usual language of labs, laboratories, parties, a system entering, then leaving a lab, There's a whole list of quotes like this in the paper, or the usual kind of language that we use about physical experiments. And then a little later, so for example in Bruckner's papers, not the first papers from 2012-13, but in his later papers in 14-15, and also I spent some time in Vienna working with them in 2013, we've talked about these things very much. And Bruckner really became, so Czesław Bruckner became very careful about not saying things which are not there in mathematical formulations. So he will never again say that the system decouples from the environment and then gets back dissolved into the environment or something like this, because he understood, I mean, we also had these discussions with him, he would recognize that this is only a metaphor for somehow it doesn't make sense to talk about environment when we don't have any space-time, any medium in which this environment could become physical at all. So it's not a physical environment. Younger guys, like Amin Baumele, for example, he would still talk about parties, although he fully recognizes that his own work on three-party situations puts into question this idea that what we're talking about can be even interpretable in terms of local parties, with local labs and whatever they have there locally. So these people, again, I think that the interpretation as being without systems is fully mine. You cannot find it in any paper by Czesław or by Amin or by anybody else in this area. But I think that they have realized at some point, and we've had a lot of discussions with them also about this, that this metaphoric language is really only metaphoric, that you cannot be serious about this local labs language.
Just a follow-up about what you just said. You cannot be serious about local lab language because they are not embedded in a...
Yeah, you can be serious about local labs in the sense that you can say that there are inputs and outputs, but you cannot say that there is a system sort of flying into a lab and then flying out into the environment.
Because they're not embedded.
Yeah, so we still have observers, okay? So we still have observers in the sense of local observers, but this idea that the observer has somehow a lab into which this system flies in and flies out is only a metaphor. But yeah, we definitely have observers. So in this language, inputs and outputs are indexed by observers. So yeah, and it's an interesting question which I'm trying to work on right now, is what happens if you don't have the same number of inputs and outputs. So imagine you have 2 inputs and 3 outputs. Can you interpret this as how many observers? And that's a big question that I'm trying to work on now. So how do we generalize this? If we don't have an equal number, so we cannot say that there are 3 observers, can we still talk about some physics or some kind of theory? And I think that yes, we can.
I have a more general question about your new meaning of physical, or this kind of new mode of thinking about systems, or not thinking about systems. What would you say to someone who would have the impression that all this might amount to giving up some kind of descriptive ambition that a standard realist might have towards the physical theory as standard becomes true?
Yeah, so I'm talking, by the way, in the article about how you would explain this to a naive realist. And there is a paragraph about that. I think that this idea of constitution of systems under certain conditions makes sense. So I haven't said that systems have to be thrown out in trash. I said that under some conditions, it makes sense to ask this question: under which conditions can we interpret these inputs and outputs as being about systems, as having some aboutness? But under other conditions, it cannot be done. So a physicist, I think, will understand this, that under some conditions, the strings of inputs and outputs can be read as being about some system traversing my lab, and under other conditions they can't. Another name that I should quote here, which you of course know about, is Lucien Hardy, not only for his axioms, but for the causaloid framework. So Hardy, in his papers back in 2006, 2008, when he's trying to propose an operational approach to quantum gravity, right? That's his idea. Basically, it's a very similar idea. In quantum gravity, how can you be operational? Operational means that you have inputs, outputs, and probabilities of the outputs given the inputs. But because this is quantum gravity, you don't assume that these are somehow linked by local labs or whatever, because there is no such thing in quantum gravity. So Lucien, back in those years, asked this very interesting question. How can we be operational about quantum gravity without any space-time in the background, without any notion of locality or anything like this? And basically, device-independent thinking is a version of that question that Lucien had asked 10 years ago.
Mm-hmm. But how does it go beyond the kind of operationalist way of thinking about physical theories?
It does not.
Okay.
It does not. But the mathematically and conceptually interesting question here is, can we, by looking at these strings of inputs and outputs, can we see in them some geometric structures that correspond, for example, to spacetime, or correspond to some kind of locality idea, or correspond to the Tirolson bound on the Bloch sphere? And this is a difficult question. I don't have a good answer to this, but this paper from 2015 gives some answers, which I admittedly know are very debatable and incomplete. But I think it's an interesting research topic, and actually it's my kind of research program, to look at these strings and to ask the question, well, under which conditions do they exhibit contextuality, non-locality, quantum features, continuity of transformations between pure states? Can we talk about such things? Because if we don't have that, we don't have quantum theory. But also it might be an interesting question to see under which conditions they can be interpreted as coming from something that lives on some manifold. And I think that if we take these strings as fundamental ingredients of our theory, we can actually ask a lot of questions that pertain at the same time to quantum and to gravity.
Yeah, I have a question as well. So I think I didn't understand how you said that there was a program to reconstruct quantum theory from basically different axioms and the standard ones. And then you said there was the 5 axioms of Hardy in 2001. Later, you said that another open problem was whether you can recover the Tirolson bound.
Yes.
And that there was many attempts and nobody succeeded. I didn't understand how it doesn't follow from Hardy's.
Oh yes, okay. It does follow. It does follow. Simply people are not happy with Hardy's axioms.
Okay.
Yeah, of course it does follow. So if we have Hardy's axioms, they come in 2 versions. So I showed you 6 axioms saying there are 5, because the 5th one comes in 2 versions. But the problem is the 5th one, it's a continuity axiom. So if you have continuous transformations between pure states, then you just have quantum theory. That's it. 2 square root of 2. No debate. So it's a bit too much to assume continuous transformations between continuous reversible transformations between pure states, because then the Tirolson bound is built into it. Mm-hmm. So forget that axiom. Go to a landscape of possible models that can be some of them can go beyond quantum non-locality, beyond Tirolson bound. And the question is, okay, in this landscape of modals, is there an axiom that takes us directly, it stops us at 2 square root of 2, not more, not less? And the answer to that is, well, people have tried. Information causality is a very good attempt to do so, which fails in, I think, 1 case out of 64, something like this. So it almost answers the question, but almost. It's a very good answer. There are different other answers. But of course the idea is don't postulate at the outset something that just takes you to quantum theory, but take a bigger framework which can accommodate quantum correlations but also other correlations, and ask specifically, can we in this framework formulate an axiom that will take us just to square root of 2? And that's a very difficult question. Nobody really has a... And the answer to this question is you can't do it because there's a theorem from 2011 by, I'm forgetting whom, which proves that you cannot characterize quantum theory by bipartite constraints only. So now there's more or less a proof that any set of bipartite constraints, meaning Alice and Bob only, will never get you to quantum theory in full. So you have to have, and it's an open question, you have to have more than bipartite, but is it enough to have tripartite or not? Do you have to go to all n? It's an open question, nobody has an answer to that.
Could you move the microphone a little bit closer to the audience?
Yeah, that's kind of a naive question of understanding. So, is it
unnecessary?
Okay.
Okay, let me start again. So this is kind of a naive question of understanding. So, is it okay to label your account as an operationalist then, and just purely operational after all, or would you be fine with it, or? Then I'm just wondering, isn't it kind of always a task of a physical theory to somehow fulfill an operation perspective? But then it's the remaining question whether you can tell a deeper story, whether you can tell more.
Yeah. So let me single out the assumptions of this account, and I will be happy with the term operational. Yes, I'm not sure about pure. So the foundations of this account are the following ones. You have inputs and outputs, and these are some symbols in finite languages.
Yeah.
And there is a distinction between them. You know which one is input, which one is out, and it is an output. You can say this introduces a local time error.
Yeah.
Why not? Right? Local meaning that if you know that an input and an output pertain to the same observer, it's a local time error. If you don't know that, you cannot do that. But definitely there is a distinction between two types of data, something called inputs and something called the outputs. What else?
Yeah.
What else? Well, the probability distribution, of course. But what else? Well, the principles. Yeah. So yeah, an operational approach, it has inputs and outputs, for sure. But also there are these principles. So that's why maybe purely will not be my favorite term.
Yeah.
Because it's not only about inputs and outputs, it's also about some principles which act as constraints.
Yeah.
And these constraints, there is a big question, where do they come from?
Yeah.
How do we understand, why this and not the other constraint? And that's a big debate on where principles in physical theories come from. Before we elevate them, Einstein had this term, elevate them to the status of axioms, somehow we must convince ourselves that they are our best candidates for axioms, right? Because, no signaling before Einstein, who would have thought, right? So we somehow have done enough heuristic work so as to convince ourselves that this is a very good candidate for being a principle. Right, so that's something, thanks for asking, because that's something that I've been discussing in a number of articles, and also in this recent article called The Effectiveness of Mathematics in Physics of the Unknown. So I'm trying to say that whenever we're exploring some unknown territory, it's not at all surprising that mathematics is efficient in physics, effective in physics. So contrary to what Wigner said in his famous surprising article. The reason why is that the only way to explore the unknown is through this kind of black box thinking. Inputs and outputs, in the middle there is the unknown. And how do we deal with it? Well, we try some principle and see if we can recover the probability distribution. Then we try some other principle and see if we can recover the probability distribution. So this is how we're trying to make a theory of the unknown.
Yeah.
Right, so where do these principles come from? Well, from our previous heuristic work in physics, and also from our trial method. And that is why I would not say that this is purely operational,
Right.
because it's operational plus this big question: where do principles come from?
Yeah. But is the general claim now that physics talks about stuff, so to speak, very general levels through some kind of operationalization and some kind of principles built into that operationalization?
Yeah, the difference here is that physics is not talking about stuff.
Yeah, okay, sorry.
Physics is talking about languages.
Yeah. Really, so, but we could not say, yes, physics talks about languages, but is it all? Why doesn't it talk about meaning? Why doesn't it even talk about meaning? How do you rule out that it talks about stuff after all?
Oh no, under some conditions these languages will be interpretable as being about stuff.
Yeah.
But I'm saying that's not the most general situation.
Yeah.
So rather than saying physics is about stuff, you should first say physics is about languages, and then ask under which conditions can we interpret it as being about stuff. And the stuff is not real world entities. The stuff is theoretical entities in your theory, right? So that's not entity realism. That's stuff in your theory. So these are theoretical constructs.
Yeah, okay, thank you.
Yes. So, okay, now I don't understand the teacher's main philosophical thesis. Because I think I understood a strong claim, which I thought was a claim at the beginning, which was an argument against what we call naive entity realism. So, in this strong claim, physical systems do not exist. They're just languages floating free. And then there is maybe a weak view, which is that sometimes you can have like a mathematical apparatus which resembles that of ordinary quantum theory, but which cannot be physically interpreted. It seems that the first thesis is really, really strong and philosophical interest. The second one, which seems more defensible, is maybe mathematically interesting, but
okay, so let me distinguish a couple of different theses in what I've said. The first was a non-thesis against entity realism and naive realism and all that stuff. I'm not here inventing any arguments about entity realism. These have been invented before us. So entity realism in the PR sense, or Einsteinian, pure Einsteinian sense, cannot stand for Bell inequality reasons, for Köppen-Specker reasons, and for all these other reasons.
okay, maybe
that's not my argument.
Just define maybe
Now,
entity
my actual thesis was that even within a theory, so let me call these entity things, let me call them objects, and let me oppose them to systems. Now, a system is a theoretical entity, not out there in the real world. It's a part of my theory. I'm saying a state of a system. When I say that, in my theory there are systems. So these are constructs in my theory, not in the real world. I don't know if they relate to the real world, that's a different question. But in my theory, I usually have systems. And definitely for me, Einstein had never envisioned a possibility of not having systems in a theory. Or, I mean, Bohr, I'm not sure he has ever, well, it's debatable about Bohr, like Jesus Christ has seen it all. But anyway, so my thesis, first of all, is that you can have a theory, a physical theory, without systems. And that's, I think, quite new with device-independent methods. A physical theory with no physical systems? What is that? Now, what is that? And that's another thesis, is this claim that a physical theory can be quote-unquote about languages. Why quote-unquote about? Why I'm not saying about openly? Because this is not a semantic aboutness. right? They're not about languages. They are strings in certain languages. So under some conditions, this is the question by Niels, under some conditions, these strings in languages can be interpreted as being about objects, about systems, objects in the real world, or systems in the theory. But under some other conditions, they can't. So the philosophical claim, I would say, is that we can go way further than any debate on any kind of realism. This is not about realism. This is about the theory, not about the real world. And we can have a physical theory with no systems, physical systems in this theory, without even asking what happens in the real world. So I'm not even there.
Yeah, so you never explain why it should be called a physical theory, except for the fact that it's developed by people.
Oh no, because for a bunch of reasons, which are all debatable. So first, I think that the workings of this box, as long as we use these boxes to find out something about our experiments, and we definitely do, because there are lots of people using PR boxes to find out stuff in experiments and so on, and there's a whole world of that. As long as we use these boxes in doing experiments, we take the workings of these boxes not to be miracles, to be something different, not miracles. This is a territory of physics if we're doing experiments with these ideas around these boxes. So your question is a good one. Why is this not some fantasy pastime? I mean, some fantasy, or just pure mathematics. Well, in the same sense as I would say, in the same sense as Einstein's principal theories have ended up being explanatory at the end of the day. He thought it was just a mathematical exercise. Well, no. We think that it's explanatory at the end of the day. And I think that these things that we're doing in device-independent framework are explanatory at the end of the day, because we do cryptography, we do boxes in foundations, Bell inequality measurements and stuff. So at the end of the day, they provide explanation. And I'm only left with one option, to call that a territory of physics then.
So, I have a question, if I may, to go back to your illustration with the causal ordering that gets mixed up.
Yeah.
And so it seems as if we have certain, trying to abstract away from the specifics of the physics of the theory there, but if we have a certain kind of setup, what we no longer have are objective causal orders. What we don't have is objective global time orders, things like that. That goes out of the window. And I would like you to tell me again, I guess, because I missed that part a little bit, how from that, from the observation that this is the case, we get to there are no systems there.
Yeah, so this is similar to the next question.
One alternative could be, of course, that we say, no, there are systems, except that there's no global causal order, there's no time order, perhaps. That might be an alternative conclusion that we might be driven to, rather than saying that there are no systems.
Yeah, so this alternative, this takes us a little back to the next question, but it would be good to sort of underscore three reasons. So the first reason is that as I said, that we cannot treat this environment in any consistent way. So if we talk about systems entering labs and then going back to the environment, we somehow have to separate, what does it mean that the system enters the lab? Somehow a bunch of degrees of freedom, which we call a system, photon maybe, polar radiation or something, enters the lab and then goes back. So these degrees of freedom between the input time and the output time inside the lab, we maintain their separation from the environment. Okay, so a system is inside the lab, it's a system. So their separation of these degrees of freedom from the environment is somehow maintained from the input time to the output time. The problem is, if we want to separate these degrees of freedom from the environment in a situation when there is no global time order at all, it's not quite clear how we can even maintain something or maintain the separation of degrees of freedom. Because sometimes you have a system in the indefinite causal order framework, sometimes you have a system which goes through a lab and then goes again through a lab. So it's kind of bizarre how you maintain the separation of these degrees of freedom. This is reason number one. So there's a discussion, this is not the only reason. The reason number one is maintaining a separation of degrees of freedom in the absence of any temporal order is a bizarre idea. I'm not sure what is maintaining if there is no time. That's the first one. The second one is entering twice. It doesn't happen. So in the indefinite causal order framework, systems, so to say, can enter the same lab twice. The same lab, the same system enters twice. It doesn't happen physically. In physics, we don't have that. So it's bizarre to talk about systems entering the same thing twice. Thirdly, there is the story about three and more parties, when we cannot even talk about sort of a classical setting cannot be interpreted. Even a classical probability distribution cannot be interpreted as entering entering some labs and leaving some systems entering labs and leaving some labs. These are three reasons. Now, finally, the fourth reason is yet another one. And again, I understand that these reasons are of different persuasive power. So I'm listing, maybe each one of them would be too weak to have this conclusion, but I'm piling up different reasons. And the final reason is, again, not of my invention, is a usual reason that if you have a system propagating from an input to an output, you want to be able to tell a history of that system. So the system at time t1 does this, at time t2 does that, and so forth. And we know from post-selection paradoxes that that is not possible. So even this language of system propagating from the input to the output in quantum theory, because of post-selection paradoxes, is a metaphoric language. That sometimes, the measurement will completely rewrite the previous history strictly in the past. So that's yet a different kind of reason, not connected to the first one. So I'm saying, once again, it's not like the almost quantum correlations case when it's sort of simple. It's tensor product or no tensor product. Here we are faced with the problem of interpreting this framework of process matrix and finding a language in which to couch the linguistic expression of what is going on in the process matrix framework. And I'm saying there are all these different reasons why it is only metaphoric and not more than metaphoric if we talk about systems entering and leaving labs.
Right. Okay. Good. To me, many of those reasons sound a bit like maybe we shouldn't give up talking about systems. These are still theories about quantum systems. What we should be giving up is talking about those as systems in space and time, that somehow fundamentally these degrees of freedom are identified and separated from one another, from other systems and from the environment in spatial temporal terms.
Okay, so here's my Greek, ancient Greek quotation in the paper. Einstein actually, before we get to Plato, let's talk
quite Einstein. Einstein, in his very late writings, so really in the 50s basically, in correspondence, in his private correspondence, he is trying to kind of make sense of how do sense impressions give rise to objects. And he's writing quite a bit about this. So we can translate this in our language if we say sense impressions are really inputs and outputs, and then how do they give rise to systems. So an interesting idea from Einstein is that when he's talking about sense impressions and objects, he arrives at this conclusion that you cannot really define an object through sense impressions. There is always a leap, always a jump. So there is no definition, he says. It's only kind of gives us a heuristic, an explanation, an understanding, but not a definition. So I think it's a very important lesson. Systems don't have a definition. I cannot define what a physical system means. What is a physical system? I don't think that it's possible to give a definition. But I can give a kind of heuristic explanation of what it means that there is a physical system. It means that there are some degrees of freedom that are separate from the rest. What is the rest? Environment, measurement devices, whatever is the rest. So if we maintain this separation, and this is really a Platonic idea. Really, Plato, in I'm not sure which dialogue, is very clear that this is a constitutive move of separating and maintaining separation. This is how you define objects for Plato. So, because we cannot give a definition of system, I think we can give the best thing we can do is kind of give this explanation of what a physical system is. It's when we have some degrees of freedom and maintain their separation from the rest. Now, maintaining is fundamentally a temporal idea, some kind of maintaining in some kind of time. And this time can be, again, not maybe this time of background space-time, but some kind of other formal temporality or whatever it is. But you're right, if we don't have a space-time, it's very difficult to talk about maintaining the separation of these degrees of freedom from the rest. So we have to ask this question: if we have a system without a space-time, how do we maintain its identity? In what do we maintain its identity? And these are questions that are open to mathematical analysis.
Okay, I'm afraid we have to wrap up. Please join me in thanking Alexei once again.